Numerical solution of ordinary differential equations. Differential equations are used to model problems in science and engineering that involve change of some variables with respect to another. So in common real-life situations, differential equations that model problems are too complicated to solve exactly. Two approaches are used to appropriate the solution. First approach is to modify the problem by simplifying the differential equation to one that can be solved exactly and then use the solution of the simplified equation to approximate the solution to the original problem. Second approach uses methods for approximating the solution of original problem. So up to this point, we can say that differential equations are used to model problems in science and engineering that involve change of some variables with respect to another. In common real-life situations, differential equations that model problems are too complicated to solve exactly mean analytically. So if we say about that the differential equation is solved exactly, it means we have solved analytically and this solution is not a numerical approximated solution. So two approaches are used to appropriate the solution. The first approach is to modify the problem by simplifying the differential equation to one that can be solved exactly mean analytically, okay, and then use the solution of this simplified equation to approximate the solution to the original problem. So in this approach, like we use the derivatives. For example, if we have a polynomial of degree 3 and we take a derivative, so this will reduce the polynomial to degree 2. So that we can say that we have simplified the given problem into a simpler form. Similarly, if we integrate the problem, so it will increase the degrees. So second approach uses methods for approximating the solution of original problem. Second approach uses methods for approximating the solution of original problem. So this second approach may be use some techniques to approximate the solution of original problem like a numerical approximation or other approximating tools given in the numerical analysis or numerical methods. Or we can even use the software like Maple, MATLAB, okay, to approximate the solutions. So it depends on the user how he would like to solve the problems. While numerical techniques for ordinary differential equations are very powerful and can be applied to a wide variety of problems, it should be kept in mind that such numerical methods can have inherent difficulties of their own. We can say rather there are many numerical techniques to solve the ordinary differential problem, but still we can face some problems which are inherent by the ordinary differential equation. So numerical techniques are powerful and flexible tools and they are applied to extremely complex and possibly poor behaved differential equation. So still we are lucky that we have a numerical techniques which are in some way very powerful and flexible tools that they can be applied to the different ordinary differential equations, and even they can be applied to extremely complex ordinary differential equations and possibly poor behaved differential equation like if we have ill conditioned system, we can turn this ill conditioned system to well conditioned system to apply the numerical techniques. All problems involving ordinary differential equations must fall into two categories. So we can say the researcher or scientist divided this ordinary differential equation into main two categories. For example, that is, what are these two categories? So one is the initial value problems and the other is the boundary value problems. In what are the initial value problems? So by an initial value problem, we mean a differential equation together with enough given values of the unknown functions and its derivatives at an initial point x equal to 0 to determine the solution uniquely. Okay, by an initial value problem. So what is initial value problem? So actually a differential equation together with enough given values of the unknown functions and its derivative at an initial point. So this initial point could be taken as x not equal to 0, or even we can set other than 0. So it's not necessary to take the initial point as x is equal to 0. Okay, but in a majority of books, the initial point always taken as x naught is equal to 0. But it is not necessary to take this initial point as a 0. Initial value problems are those for which conditions are specified at only one value of the independent variable. So this is very good statement. So we can say that, so actually the initial value problems are the problems for which conditions are specified at only one value of the independent variables. So if the differential equation is given in y and x variables, so normally we consider the y variable as dependent variable and x as an independent variable. So it is easy to understand. And so the initial value problem are the problems for which conditions are specified at only one value of the independent variable x. So these conditions are termed as initial conditions, whether or not they are specified at the point where independent variable is actually equal to 0. Usually 0 is taken for simplicity. So this we need to keep in mind that it is not necessary to take the initial point at x equal to 0, but the necessary condition is that so one value of the independent variable. The condition must be specified at one value of the independent variable. So these conditions are termed as initial conditions whether or not they are specified at the point where independent variable is actually equal to 0. A typical initial value problem might be of the form as given below. So we can write a is a coefficient and the second order derivative of y with respect to t plus b as a coefficient, the first order derivative of y with respect to t. So then c as a coefficient into y is equal to g as a function of t. So obviously this t is the independent variable, and on the right hand side the function g is a function of t. A, B, C are the coefficients and y is the dependent variable. So what are the initial conditions? If you are observing that the value of the condition is given at t is equal to 0. So if t is equal to 0, value of the dependent variable will be considered as y naught. And here again for t is equal to 0, the value of the first derivative of the dependent variable is again given by v naught. So just observe that in both conditions, so we have the values at one value of the independent variable. So independent variable is 0 here and is 0 here again. Both conditions are specified at t equal to 0. So that is why this problem is considered as initial value problem. Now boundary value problems. So physical problems that are position dependent rather than time dependent. So they should be then physical problems that are position dependent rather than time dependent are often modeled in terms of differential equations with boundary conditions imposed at more than one point. So if you can also say that if the boundary is the conditions of the differential problem is not specified at one value of the independent variable, so then it will not be initial condition. So it could be boundary conditions. So we can say that in boundary value problems, the conditions are specified more than one point. We can revise again physical problems that are position dependent rather than time dependent are often modeled in terms of differential equations with boundary conditions imposed at more than one point. Boundary value problems are those for which conditions are specified at two values of the independent variables. So at least boundary value problems are the problems for which conditions are specified at two values, mean more than one values of the independent variable. A typical boundary value problem might be written of the form as given below. So d is the coefficient, the second order derivative of dependent variable with respect to t. So again the e is a coefficient, so first order derivative of the dependent variable with respect to t plus f is a coefficient and dependent variable y is equal to h is a function of t. And note it well that here so t is equal to 0 and here so t could be it could be taken any value. T can be 1, 2, 3, so on. So it depends on the problem that what is the exact value or what is the given value of t is equal to y1. So this is the example of boundary value problem. So next we can study Euler's method. In practical, several first-order differential equations considered to be difficult or cannot be solved by analytical methods. To deal with such equations, Euler's method is useful. In practical, several first-order differential equations considered to be difficult or cannot be solved by analytical methods. So to deal with such equations, Euler's method is useful. The problem with Euler's method is that you have to use a small interval size to get a reasonably accurate result. So suppose we wish to approximate the solution to the initial value problems given as dy by dx, f of xy. So this is a function of two variables x and y. So dy by dx is the derivative of y with respect to x, and what are the condition is y at x naught is equal to y naught. The idea behind Euler's method is to use tangent line to the solution curve through x naught y naught to obtain such an approximation. So equation of tangent line through x naught y naught can be written like a straight line. So the equation of straight line is through the point x naught y naught can be written as y of x is equal to y naught plus m x minus x naught, where m is the slope of the curve at the point x naught y naught. That is, m can be written as f of x naught y naught. Equation 7.2 takes the form y of x is equal to y naught plus m can be replaced with function at the point x naught y naught. Setting x is equal to x1. So this x, if we replace this x with x1, gives Euler approximation to the exact solution at x1. Therefore, equation 7.3 takes the form which can be written as y1. So y at x1 can be replaced with y1 is equal to y naught plus h f of x naught y naught. So where we can say that x1 is equal to x naught plus h. So this x1 can be replaced with x naught plus h. Then x1 will be vanished with x naught will be vanished with x naught, because if you replace this x with x1, so then next we can replace this x naught plus h minus x naught. So we will have here h, and after this equation will become like 7.4. So it is easy to remember this Euler's method. So thus just y1 is equal to y naught plus h f of the function at x naught y naught. So yeah, you can just remember like the function at the point x naught y naught multiplied by h plus this value y naught and the second value. Now suppose that we wish to obtain an approximation to initial value problem at x2 is equal to x1 plus h. We use same idea except modifying slope of tangent line as given below. So if we replace this, if we want to calculate the Euler approximation to the next point, which is x1 plus h. So y of x can be written as y1. So we replace here yx is equal to y1, this one. So function value at the point x1, y1, and x minus x naught, x1. So then this will be y2 is equal to y1 plus h f of x1, y1. So just see this one. So y2 is equal y1 equal to y naught plus h f of x naught y naught. So this will be like uh, this one. It will take the form of y2. So y1 is equal to y naught plus h f of x naught y naught, and y2 is equal to y1 plus h f of x1 y1. So where we can say that x2 is equal to x1 plus h, or x2 can be written as x naught plus 2h. Continuing this way, we get sequence of approximations to the solutions of initial value problem. Okay, this one 7.1 at point xn plus 1 is equal to xn plus h given by. So in this way, we can get a generalized form of the Euler's method like this one. So yn plus 1 is equal to yn plus h. So value of the function at x and yn, where we can say that xn plus 1 is equal to xn plus h, or xn plus 1 can be written as equally x naught plus nh. Okay, so easy to solve the problems with Euler's method. For example, if we are given that solve the following initial value problem using Euler's method and approximate at x is equal to 0.1 by taking h is equal to 0.02. So how it works? So this is the function. What is the function? Dy by dx is equal to y minus x over y plus x. So observe that x is equal to 0. So that is why this is initial value problem, because we're given only one value of the independent variable. And we can write Euler formula in the form of k or n. It depends on the users. So it is written in the form of k, yk plus 1 equal to yk plus h f of xk yk. Start by taking k equal to 0. Then the equation 7.9 becomes, so replace this k with 0. We will have y1 equal to y naught plus h f of x naught y naught is equal to, so what is the value of y naught? So value of y naught is here, this one. So value of y at x equal to 0 equal to 1. So this y naught, this can be replaced with 1. Okay, so I need to calculate this h. H is given here 0.02, and then we replace this y with y naught, x with x naught, y with y naught, x with x naught. So what is the value of y naught is 1. So replace y naught with 1. 1, 1. What is the value of x naught is 0. So this 0 is the value of x naught. So in this way, we have calculated the first step of the iteration. So this formula works as the iterative formula. Okay. And next, we will increase the value of k for k equal to 1, and this formula will take the form as y2 is equal to y1 plus hf of x1 y1 equal to 1.02, because now it will replace y1. So this is the value of y1, 1.02. So this will replace there. So h is the same, and then Uh, here, this should be y1, x1, y1, x1. So here is a mistake. This should be y1, x1, y naught, x naught, x1. Okay, so we replace this value y1 with 1.02 and x1, okay, with 0.02. Then we have calculated it's 1.0392. Similarly, we can compute